welcome to week 11. We talked about penalty methods and a bit about the interior point methods this week. So let's first start with assignment questions, and based on the time that we are left with, we will solve some other questions as well. Okay.
Yeah.
So I hope you are still able to see my screen.
Yeah, it's okay, fine. Carry on.
Okay, so right, question 1 is saying I have a sequence xk. The limit point is x star, and xk is basically obtained by solving f of x plus ck norm h of x squared, and we have ck going to infinity. We have x star as the minimizer of the actual problem that you want to solve. So okay, so the question is if x star is this limit point of the sequence xk obtained by minimizing these problems where we are adding the norm of the constraint and solving this unconstrained optimization problem to get the xk. If we get that sequence xk such that x star is the limit point of this sequence and ck is blowing up, then the claim is x star is okay. I think I wanted to ask something, but I instead ended up writing it, so sorry. I meant to say x star is feasible for the problem. So let me just cut this here. Oh, that's strange, just vanished.
Yeah, this is a bug in the software, maybe.
Yeah, okay. So anyway, let me just write it down. Yeah, so this is the claim. So is it true or false?
Yeah, this is false.
This is false. Why is that?
Yeah, means this follows from the theorem which he mentioned during the class, right? They converge at the limit point to the Lagrange multiplier of the constraint, not necessarily to the optimal solution.
No. So okay, so there are two things, right? So let me see the statement again. Right. So what does the theorem say that we saw in the class?
Yeah, the theorem said that if we take any subsequence of the original sequence that tends to infinity,
Sorry,
then
if we
for
take
if we take any subsequence, then for any such subsequence, the limit point is approached to the Lagrange multiplier of the corresponding constraint. That is what the theorem stated.
But we are not in that setting, right? So that what you are saying, so there are two parts to that theorem, right? The theorem that says that if x star is a limit point, right, obtained by
Yeah,
xk, the sequence xk. Uh, so we are in this setting, right? We are given that x star is a limit point, and we are saying that xk is obtained by minimizing that. Okay, fine, sure. Then there are two parts. If x star is infeasible and if x star is feasible, there are two parts, right?
yeah.
So in this case, you end up getting to stationary point of h of x star, sorry, norm of h of x, and here you have this whole long statement, right, about reaching the optimal Lagrange multiplier value.
Yeah.
So how do we argue here?
So what the question says is, question is saying, which is not right. Is feasible for the problem. Yeah, when we minimize this thing,
Hmm.
which is mentioned in the question,
Right.
there there can be two possibilities, right? Uh,
Uh,
so we can either reach a stationary point of norm of hx square.
right.
So, but we cannot guarantee in any case that it will be an optimal solution, right?
Uh, so that statement requires you to assume that x star is infeasible, right? So
X
what
is
I'm
a limit
saying is
point.
you are in this setting, right? So, but the question isn't the question asking about this feasibility or infeasibility of the point x star.
Just give me 1 second. I'll just read through it once. X is a limit point. Yeah, it's asking about to identify whether this limiting point is feasible or infeasible.
Yeah.
X is infeasible. X is feasible. On a constraint negative point of constraint. Then that means if the LICQ conditions hold, then we can guarantee that X star will be a KKT point, right?
So here there's only one constraint.
Yeah, so we forget about LICQ.
Yeah.
Yeah, so we can guarantee that X star will be a KKT point, not that X star is an optimal solution, right?
See, here we are only concerned about feasibility. We are not even going to the KKT conditions. We are just asking for the feasibility of the point of this limit point x star. So what we are given is there is a sequence xk that is obtained by minimizing these. Have I written this? Okay, yeah, I have written this. I minimize this sequence of unconstrained optimization problems. I get these xk's, ck's I keep on increasing, and I get this xk sequence for which x star is the limit point. So then can I say that x star is feasible for the problem, for the actual problem, which is this? how to argue in this case.
But the point is, just by minimizing this entire thing, entire objective function, what we are given, we cannot guarantee that what we reach will be a feasible point, right?
Yeah, so correct,
Yeah, we
but
cannot
what can
guarantee
we?
that.
So what is it that we can say in this case? That's what we want to know, right?
Yeah. We can either say then that we have reached a stationary point of the objective function square.
Can you say that again?
Yeah, means from the first part of the theorem, which says that if x star is infeasible, then we reach a stationary point of norm h of x square.
Right.
So that is one thing we can say.
No, but see, the thing is that statement assumes that x star is infeasible. Here we are asking whether x is infeasible or not. See, that theorem that you're referring to, it says that under the condition that whether x star is feasible or infeasible, you have so and so happening. Let's say stationary point of h of norm of h of x squared, or that corresponding condition of ck
Yeah,
hj xk equal
yeah, I
to.
get that. Yeah, I get that. But it looks kind of strange. Yes,
Okay, so maybe we'll come back.
let's see.
Maybe
Let's
we'll come
see.
back to this. I just let's think over this. Okay, we can come back to this. I just want you to think about how to argue in this case. Whether all the information is given, if the necessary information is given to be able to guess the answer here. If so, what is the answer? So we'll come back to this. Let's continue with the next question. So this is my feasible region S, right? So,
By the way,
yeah.
before we embark on this question,
Yeah.
I just wanted to ask you where we can obtain the proofs of these theorems. They are pretty lengthy and mouthful.
I am not sure actually. I have not seen these proofs before. I'll have to check and get back to you on this after the
Yeah,
discussion.
because he quoted quite a lot of theorems without any proofs whatsoever. Even any idea of proof how to go about this. That's why I was asking.
Yeah, I'm not sure. I'll check and I'll get back.
Yeah, sure. Please make a note of that. That's all right.
Yeah, okay. So, coming to question 2, we have some feasible region G of x equals to 0. Okay, we have G is continuous. The question is, which of the following cannot be used as the penalty function? Yeah, so these are the 4 options we have. So what do we need to check for it to be a valid penalty function?
Yeah, Yeah, the basic criterion is that whenever x lies in the feasible region, that penalty function should vanish.
Okay, so one second. So there are three properties, right? One is what? P of x is continuous, right?
Yeah,
What about the next one?
but when Professor Kulkarni was using an L1 penalty, that is not. Ah, okay, that is continuous. Okay,
Yeah,
non-differentiable.
we're not
Ah,
talking
okay,
about
okay.
differentiability.
Yeah. Fine, fine. Sorry. Yeah.
So
So
there are,
yeah, that is non-negative, and
yeah.
yeah,
And what's the other one?
and it should be equal to 0 if and only if x belongs to S.
Right. So okay. So now that we know that these three are the conditions, so what can we say? So remember that the constraint is an equality constraint here.
Yeah.
So what can we say?
So this, yeah, we just try to see when if gx gx is equal to gx lies in the feasible region, satisfies the constraint. What the give? Just compare those options.
So let's just go step by step. So for the non-squared case, 1 and 2 are obviously satisfied.
Yeah,
And what about the 3 case? That's also true, right?
three.
It's a norm, so that's just holds true by definition. What about modulus of g of x?
Yeah, that's also
Same thing, right?
satisfies those this condition. Yeah.
Okay. How about the next one, which is I think max function? Yeah. So max of g of x comma 0.
Yeah. So here one will be satisfied.
Correct, because z is continuous.
Yeah.
Right, and
Uh, two two is also satisfied. Yeah.
correct.
But three, I'm not sure. I don't think it's satisfied.
Okay, so is it possible for g
Yeah,
of x to have
yeah,
some non-zero value?
yeah. I'm trying to.
I mean,
So if
for
gx is
example,
some.
let's say g here, let's say takes a negative value, g of x for some x.
Yeah, that's what. Yeah.
So then
So
max
that's
is
a
what?
simple example.
0, but then that doesn't
Max is
mean that
zero.
x is in a
Max is
physical
zero.
region, right?
Yeah.
So what I'm having is 1, 2, but unfortunately 3 doesn't hold, right? So similarly D I think to satisfy all of these things. So I mean,
Yeah. D is the same story.
is it? So it's continuous,
So
but
yeah, it's
will it
continuous.
satisfy it?
No, that it goes in the other direction.
Yeah, exactly. So
Suppose
yeah,
we take mean as something positive.
yeah.
Hey, sorry, mean as
So for example here
yeah,
1 is
something
obviously
positive.
true, but then 2 won't hold true because you can just take g to be a positive quantity, right? G of x to be positive
Yes,
for
positive. Yeah,
some x, right? So what about 3?
three zero equals G is
So let's
negative.
say g of x is 0 meaning
Yeah,
x is
yeah,
in
G
S.
is. So if I take GS as negative,
Yeah,
then it's so then
you know,
it's
you can
negative.
take g of x to be positive, so in that case the min will be 0,
Yeah, positive. Yeah,
but
okay,
then
take it up.
x is not in S,
Yes.
right? So
So that is also not true.
you have AB, your A and B, and then C and D are not there. I mean, they're not desired penalty functions. Okay, so just a quick recollection of the property. Uh, okay, question 3 is saying again I have a minimization of function f of x with a equality constraint h of x equals to 0. and penalty, we have two penalty functions, L1, L2. So either the norm or just the modulus. So which are false, which are true, which are false? So penalty method with either L1 or L2 converges to some local minimum with finite value of the penalty parameter for L1. So is this statement true? False?
Yeah, this is true. Yeah, this is true.
Why is that?
This follows directly from the second theorem, which is stated during the L1 penalty.
Okay, what is the second theorem?
Yeah, when X star is a strict local minima of the constraint optimization at which KKT conditions are satisfied
Right.
with Lagrange multiplied theta j, then X star is a local minimizer of this thing for all C greater than C star, where
But we are
C
not
star
given
is
any
equal to
such things
maximum
here,
of
right?
the.
That
Yeah,
is
we are
just
not even
indicating
given
the
any.
necessary conditions. First order, sorry, not first order, sorry, just necessary conditions for X star to be a
That's
strict local
true.
minimum, right? Sorry, what
That's
am I
true.
saying?
That's true.
X star being strict local minimum of the original problem, the necessary condition is X star is local minimizer of the appropriate unconstrained optimization problem. The Q with the fixed CK for various cases. So how to
So how
argue
do we
this?
go about this? Yeah. That's what I was thinking.
I mean, it's a little hard, I understand, because these are all informal arguments here, I understand. So it's okay. I just want to have a bit of conversation before just saying, okay, this is true, this is false. That's all.
Yeah, please come once more. I didn't get you actually. What
No,
you were
so
saying.
I understand it's very difficult to give. I'm not expecting a proof. I'm just saying. So when you say that you're appealing to the theorem, we're not exactly
Uh-huh.
appealing to the theorem, but I just want to recall that reasoning. Like, what was that reasoning which led us to believe or think that, let's say, L1
Yeah,
penalty. Yeah, what's the finite?
yeah.
Yeah, why the finite value of penalty
The
parameter would be true?
basic the basic intuition which he was giving to the prof was that for a L2 penalty that is smooth, right? So there is a kind of ambivalency near the origin,
Okay,
and L1 is sharp enough at the origin so that it distinguishes the point exactly equal to zero or something not exactly equal to zero.
okay.
So if we go by that reasoning, then can we stretch it further? This argument. That's what I was thinking.
Um, for now, I think we can keep it at that. Let's see. Maybe based on the the other parts, I might ask something else. But for now, let's keep it at that. So, objective of the penalized problem is differentiable for L2 penalty.
That should be true, right?
Yeah,
Because it's a differentiable penalty. It's norm squared, so
right. So L1 penalty penalizes more severely than L2 for points far away
False, right?
from. Yeah. So this I can just by definition. Right. Okay. Penalized problem is easy to solve for L2 penalty.
Keep. I had a doubt
Yeah.
regarding these. May I ask you a ask?
Yeah. Yeah. Sure.
Indeed, there was this theorem that uh, the sequence xk that we get from solving the penalized problems,
Yeah.
any limit point of that sequence is the solution of our constraint optimization problem.
This is
Right.
from the lecture 20, right?
Yeah.
Hmm. Yeah.
And in lecture 21, for the quadratic penalty method, there is this theorem that divides the limit points into, if the limit point is feasible, then this happens. If it is feasible, then this happens. But isn't this contradictory? Like in the earlier lecture, the theorem said that whatever be the penalty method, any limit point is the solution.
Yeah, I think I agree with that. Yeah, even I noticed the discrepancy. I think that was a mistake in lecture 20. I
But
do,
then
yeah,
online,
yeah.
I researched about it and I found out that this discrepancy was there as well. Maybe there's some flaw in our understanding or something. I'm not sure.
Okay, I don't know if he implicitly assumed something about the penalty function. That's what I'm wondering. Uh, I mean, I personally, for example, don't know the proof, how to prove it. So that's why I'm not able to think what restrictive conditions might actually make it true. Uh, Sway penalty curve. Yeah, I am not sure actually. I can't think of any condition under which the theorem that he stated in lecture 20 where the limit point will be a solution of the original constraint optimization to be true.
this was in the previous lecture, right?
Yeah, the last point that he said at
This
the end of the lecture. Yeah.
Yeah, at this point, I also agree with the other person. I do not. You are Tanmay, right? Yeah. Okay. Okay. Fine. So, which Tanmay was saying that at the last instance there were a lot thrown in actually. So, lot of stuff to assimilate.
Yeah, I'm
Yeah.
just looking up whether there are other conditions that I could assume. So, Tanmay, can you just share the source maybe where you found that? I mean, as in what conditions they assumed to make that statement? Hello?
Yeah, just a sec. I will share a link here. You good. Yeah.
Yeah, I mean, I don't think I'll be able to open it here since I'm in the meeting and recording it from this side. I was just curious what conditions they have assumed to be to make that statement.
It's opening. I will tell you.
Yeah.
Okay. May I screen if that's allowed?
Yeah. Sure. Just 1 second. Let me stop sharing my screen for a moment. Yeah, I think you should be able to share your screen now.
Yeah. I hope it's visible.
Yeah.
Yeah, so this is a document of University of California, I guess.
Yeah.
There is this first convergence guarantee of the quadratic penalty
Hmm.
method, and then they've mentioned this. Every limit point is a global solution of the constraint optimization problem, and then there is a proof of this.
Okay, can you just zoom in slightly? Right, so it's the same thing that they're writing. Now they are saying every point is a global solution. Okay, xk is a arcmin of qck. Fine. Why should that xk converts to x star? I didn't get it. Every limit point of sequence. Okay, they're just
It's a
assuming
limit
calling it
point.
x star, some x bar.
Yeah.
Okay, x star is a global minimizer of star. Okay, xk is a global minimizer of ck. Okay. Right, penalty is non-negative, so qx. Oh no, qxk is a global minimizer. Okay.
The same similar proof is on MIT Open Courseware document as well.
I see.
So this holds at least.
Right,
That's
yeah.
I'm sure.
Okay.
But then they themselves on the very next
Just
page,
a second, just a second. Can
yeah,
you go to the second page? Yeah.
this one.
So they proved that okay, it's a feasible point. Hi x bar is 0, and ck going to okay, that's 0. Fine. But so what is star star? I forgot. Star. Okay, star star is just that same thing. Okay. Uh, but that does not make sense. So they took a limit, right?
Mm,
That limit step does not make sense. So what they are doing is limit of ck times hi of xk. They are writing it as ck times hi of x bar. Somehow the limit doesn't apply on ck, which is weird.
but then if it is exactly zero, then
No, that's okay. But relative growth matters, right?
but it is exactly zero, no? So no matter how CK grows,
No. See, uh, so what you are doing is you are applying the limit in the star star step.
okay.
Okay, the x bar comes after applying the limit. So they are applying limit to the product of ck and the hi of xk terms.
Oh,
So that is where I'm not understanding, like how are they able to prove it with such ease? That's what I'm concerned about. See, if you think about it, we get a very complicated statement when we are taking limits because we don't know how the h of x might behave when we take a product of it with respect with the ck terms. So you have to be very careful. You need to assume some strong things like some constant qualifications, x star being some kkd point, and then maybe you can hope to for the limit terms to be some finite quantities.
yeah.
So
The
I'm
proof
not
was a
sure.
bit different on the MIT document. I have to open it. But then if we ignore it for a moment, let's say whatever be the proof,
Okay,
just it was mentioned, right?
right,
And then there is this algorithmic framework that's given.
right.
And then convergence guarantees of the practical quadratic penalty method.
Fine.
Here they have mentioned that if the limit point is infeasible, it is a
Okay.
stationary point of the function.
Uh,
Uh,
yeah, I think it's somewhat hand wavy. I don't think it's a correct way to prove it.
Yeah,
I
possible.
mean the now that I see this, it's precisely what the professor has stated as a theorem. Instead of stating two
Yeah,
theorems, he has stated in the lecture as just one single theorem, right?
yes, yes, exactly.
But yeah, I think that statement from lecture 20 has to be removed. I'm not sure why that was left there. I think it's very misleading. Doesn't have to hold true.
Yeah. Also, for the purposes of this course, I can just ignore that, right?
Yeah. But just be careful about that limiting step. So just because it's a product, we cannot just separate out and take limit in one quantity and forget about the other one.
Yeah, yeah, I got that.
Yeah,
Thank you.
yeah,
So Deep, which Tanmay was referring to that theorem,
right.
which is just plainly professor was telling without any qualifications that it's a solution of the original optimization problem. So further qualifications need to be done for that, right?
Yeah. Yes.
Yeah,
So
I
because if
understand
you
that.
recall, ultimately what we are doing is we are uh, see secretly it is like a Lagrangian, okay. So we want some of the terms to die down and some of the terms to resemble the Lagrange multipliers. We are just finding conditions, sufficient conditions, which ensure that these terms become like those. The
Ye-
what I'm trying to say is we are getting some f of x plus some what is that summation ck summation j equals to 1 to t hx whatever it is. I mean p of x in pj of x more generally, right? So secretly, I mean, we just want this to resemble the Lagrangian. The point is, how do we make it happen?
Yeah, I get the basic point. Yeah, I guess it point. So yeah, so just a plain
But
statement wouldn't
even,
suffice.
Yeah.
Yeah, that's
but then even from that, we just get the KKT necessary conditions are satisfied. That's not sufficient to show that it will be the mean.
maybe the sufficiency is at stake here, I think.
No, I sorry, I didn't get the question.
Even from the constraint qualifications, we will just at max get the KKT conditions hold. They are necessary conditions. They are not so sufficient, right? So it
Okay,
is well.
so I'm not sure which sufficiency for what and necessity for what. I didn't get that part. So what I just clarify what I meant. So what I am saying is to be able to mimic this the q c case that we are writing q x comma c case. I was saying that let it resemble something like a Lagrangian lambda mu, whichever notation is fine. And under what conditions you put some conditions which implies this, which implies that these are similar. So that's what I meant. Being sufficient conditions. Star star.
But that goes into the realm of the augmented Lagrangian method, right? Means you try to simulate a Lagrangian
Uh,
limit.
no. I mean, idea is still the same. Point is, how do you do it with a finite ck, right? That's where
Yeah,
you.
yeah,
So idea is still
get it. We
similar.
get it. Yes.
I mean, sorry, objective is still similar. Ideas, the way to do
Yes.
it will be different.
Right.
But Tanmay, right? Or Tanay, sorry, forgot your name. So you were saying something.
Just a second. Give me a second. Can you go to the theorem for the co-quadratic penalty method in lecture 221?
Uh,
That
I don't
that gives
have
this
it with
idea
me
of
here right now.
if X star is feasible, if the limit point is infeasible, then this happens. If it is feasible, that happens.
Yeah, so since I don't have the note, I can just quickly make a note of, okay, just quickly write it down here. So xk so goes to x star, okay, and this is coming from f of x plus ck norm f of x squared. Okay, so case number one is x star is infeasible. This implies it's stationary point of norm of h of x squared. So ck goes to infinity, monotonically increasing. X star is feasible. Gradient h I x star are linearly independent. Okay, am I missing anything? X star is feasible and KKT point of constraint optimization for any subset of the natural numbers such that the subsequence converges, not subsequence, I mean such the, yeah, such some subsequence which converges to x star. Take any such subsequence. We have limit k c k h j x k equals to mu j. This is corresponding to hj x star equals to 0. Yeah, this is the theorem. So you want to ask something?
In this also, if X star is feasible, we do have this forward implication that just a sec. Um, Yeah, so if X star is feasible, then we have this that it is a KKT point, and then again my same argument before, and KKT is a necessary condition for it to be a minima.
Correct. Yes.
How do then, obviously from this we will not get to the exact minima. We will be around the boundary of feasibility because it's never really actually zero, right? That we showed later in the lecture,
Correct.
just after this.
Correct.
So still here we are assuming that that X star that we will find will be actually the local minima. KKT conditions do not guarantee you that if that will be a minima for sure. Similar case is with the with the theorem stated for the Alban penalty.
Correct.
There also forward implication that if X star is a strict local minima of the constraint optimization problem, then we have something for the
Finite
penalized
threshold. Yeah. Yeah.
then we have something for the penalized problem.
Correct.
But we will have to start from the penalized problem, right, and then find a solution. It does not state that if it is there is no reverse implication. I hope you get what I mean.
So the reason for stating things this way is that you are basically trying to characterize what you want, right? So you assume, like, let's say x star is at the very least a KKT point. So maybe assuming x star is a minimum is probably too much to ask for. Like, at least let's see, okay, like for KKT point, if I have a KKT point, what do I need? So it is keeping that in mind. You would want to prove a statement, right? See, the thing is, you have seen the condition here, so it may seem like, okay, fine, so this is what I want to prove. I could have said it the other way around, or maybe something similar. But actually, what I'm really trying to ask, so just like in the, I hope you are getting what I'm saying. So what I'm trying to say is, if x star is a minimum, just in a, let's just go back to first 2-3 weeks of lectures. So if I want to characterize x star as a minimum, how would I characterize it? So one way to do it would be to say, okay, fine, let's assume that x star is a minimum. What is it implying?
Gradient zero.
Right, I mean, whichever conditions are there, right? I mean, there
Yeah.
could be first order, second order, whatever conditions are there. Similarly, KKT we get. So that is one way of characterizing, okay, at the very least, what do I need?
Okay.
Right, so if P implies Q, that means Q is a necessary condition for P to hold, right?
Yeah.
So that's all we are trying to.
Okay.
So the reason for stating these things, so that's where the art also lies in proving. So for example, what to assume. So I don't know the proof. Again, I'm not sure how to go about this, but I guess at least for this statement that we are seeing here, probably extra, assuming extra local minimum is probably an overkill, or maybe it indicates it not giving us much. Maybe it's difficult, and just assuming that it to be a KKT point is good enough for us to get to the kind of conclusion we expect to have, which is mimicking this behavior of Lagrange multipliers in the limiting sense.
Hmm.
I was just checking a note on the phone and just wondering if I can quickly do a proof of some basic proof of these penalty convergence theorems. Just give me a moment. So, by the way, does that maybe address a part of your question, or
Yeah, it does.
okay? So let me see. Let me then take this detour for a moment, and let's take a look at this. I might make a mistake, so just let me know if at all you see something that doesn't make sense. Okay, so we start with the basic premise that we have minimize x plus ck p of x belongs to R, and this is an unconstrained optimization problem we are solving. So this thing we are calling q x ck. Okay, ck as usual going to infinity. Ck greater than equal to 0, and we will assume that ck plus 1 greater than ck for all k strictly, and the solution to this q x comma ck minimization is, let's say, xk, the argmin. So there are some claims, which is q xk ck is less than equal to q xk plus 1 ck plus 1. So I am just stating. I also want to see if they are true or not. So let's just see. Let's just not take it at face value. Similarly, the penalty is decreasing with each iteration. The q value is increasing. Is it increasing? Yeah, it is increasing. Objective value of our function of interest is decreasing, and f of x star, optimal value, is lower bounded by this, which is lower bounded by f of xk. So any thoughts on how we can prove this? We'll start with the first one. So this is our this is the q. Okay. This is our qx comma ck function, and if we minimize this, we get xk. So do you see why this is true? It's just two steps actually. Hello.
Yeah, yeah.
So any thoughts on how to go about this?
So you can just apply the basic definition. Can you go by that?
Yeah, so it's just a basic application of our definition. So by definition, q of xk ck less than equal to q xk plus 1 ck, right? Xk is a minimizer,
Yeah, yeah, yeah.
and ck plus 1 is strictly greater than ck.
Yes, yes, yes. Apply once more.
Right, so I think it should be a strict inequality. Not sure why they have written less than equal to. Okay, similarly, how about the penalty? P of xk greater than, so the claim is that this penalty P of x, if you evaluate at xk and xk plus 1, the penalty is actually decreasing. So any thoughts on how to proceed for that? So where does xk come from?
XK, yeah, XK plus means XK is an RN, right?
Okay, no. So see, the information that we have is really going to come from xk. Which solving which problem does give us xk? This problem for an appropriate
Yeah,
k,
yeah, this
right?
one. Yeah, yeah, yeah.
So
Yeah,
what we
this one.
really need to do is what similar to what we have done for proving the part 1. Ultimately, xk is a minimizer for corresponding to this qx comma ck. Similarly, xk plus is going to be a minimizer for qx comma ck plus 1. So I'm just going to use the fact that xk is a minimizer for this ck, xk plus 1 for ck plus 1, and I apply this same property that I've done here. Only thing is now I can expand. Now I can actually talk about these fx. I can actually write this q in terms of these f, p, and ck, and then see what happens. That's the strategy. Okay. So what I'm trying to
Okay.
say is, for xk, by definition, you know that this qxck is less than equal to what?
Yeah, so
Just put xk plus 1, right?
K plus one. Yeah, yeah.
Similarly, what can I do? I can look at xk plus 1 now.
Yeah, yeah. Okay,
I mean, I
okay.
can look at ck plus 1, the qxk plus 1, ck plus 1.
Yes.
Okay, so ck plus 1, pxk plus 1 less than equal to what? So I just put xk instead. Is it fine? Is it clear
Yeah,
what I
yeah,
have done here?
yeah, 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 yeah.
Okay, so what can we do now here?
Somehow I need to subtract some of them of the XK
Yeah,
terms off, right?
yeah,
If
that's what
it's
we'll do. Yes. So what we'll end up doing is we can just do that, and ultimately what we'll end up getting is ck plus 1 minus ck p of xk greater than ck plus 1 minus ck p xk plus 1. So what do we get?
yeah, we get that.
Okay.
Yeah.
Right. So I mean, you can see there's fxk here, fxk here. You can just match the corresponding terms. You can just subtract accordingly, and you'll get this. Okay. All right. So what else? What's the third one? I hope you are with me. You people are with me so far.
Yeah, it's
Yes.
okay. Yeah, yeah.
Okay. So right. So what we have talked about so far is what's happening to these values of these q values and the p values. So let's talk about the values of f between successive iterations. So far, is it making sense? Maybe except for this. I don't know if this also maybe in a way makes sense because CKs are increasing. But at least these two I hope intuitively make sense. If I am going closer and closer to the feasibility region, then I better hope that my penalty is getting smaller and my function value is getting smaller. And like you might have heard in the previous lecture 20 last week lecture. So here we are approaching from below. Like f of xk is upper bounded by f of x star. Generally we decrease, right? Here we are going approaching from the bottom, so to speak. So this is maybe one way of uh, seeing this for ourselves when he made that comment, approaching f of x star from the bottom. So anyway, let's come back to this part. So how do we do this? Again, f of xk and f of xk plus 1. So what information do we have with us?
So we try to use the fact about the penalty, right, that we derived in the previous
Yeah,
class,
so
and
naturally,
try to
since we have
somehow
used this, we have proved this 1 and 2, so we will obviously use this here in 3,
yeah,
right? So
yeah, we
for,
try
for
to eliminate that PK term. Yeah.
yeah, so for example, we let's say start with this, and hopefully this relation simplifies the expression in the first term, and then let's see how it goes. So what is the first one saying? That the penalty increases when I go to k plus 1, right? Sorry, the overall objective value qxck that increases. Is it fine? So let's
Yeah.
let's just try this. Let's see what happens. So from 1 we have q of xk ck less than equal to q of xk plus 1 ck plus 1. So I'm just writing that f of xk plus ck q sorry, not q, p xk less than equal to f of xk plus 1 plus ck plus 1 p xk plus 1. Okay, and pxk plus 1 is upper bounded by what?
P xk, right?
Sorry.
Pxk plus 1 is upper bounded by pxk, right?
Correct, right. So okay, so let me ask this way. So what is this, what between what quantities do we want to find relation? F of xk and f of xk plus 1, right?
Yeah.
So we have these terms here. So what do we do? How do we simplify our expressions? What all things can we use? So what do we know about ck?
It's monotonically increasing.
Right. Okay.
So
Yeah, so then what can we do in this case?
if ck plus 1 is higher than ck, and pxk is also known in some situation.
Can you go to proof of one
Yeah,
second?
yeah.
Okay, I think I did not write justifications, but let me write that. Cos xk minimizes qxck, and because ck plus 1 greater than ck. Yeah.
If you expand the first inequality here,
Uh,
try to expand. Maybe that I think then we can be, because then the ck the will be the same.
Correct. Yes. So you're right. That's the thing which is needed. So what do we really want to check? F of xk plus ck pxk less than of xk plus 1 plus ck pxk plus 1. Now what can we say?
Penalty at xk is greater than k plus 1. So what is, yeah.
Right, that's all. So we are done here, or are we? It's correct, no?
It's okay. It's okay. We're done, I think.
So this makes sense. Why? Okay, we'll see in the next step. By the way, is it fine? Is this step okay? Does
Yeah, it's
any?
okay. It's
Yes,
okay. It's okay.
yes, it's okay.
Okay, so another hint that actually we are increasing. So we are approaching f of x star from the bottom. Okay. So 4 would be something that we would hope for. Well, except for this middle part, f of x star being lower bounded by f of xk. That's something that we would expect. At least we would somewhat hope, given that we are noticing an increase in the value of the objective function f. Right. So yeah, what can we do now? How do we prove this? So again, the same thing. We have to obviously use the fact that xk is the minimizer for this q xk ck. It contains the f of xk, and obviously f of x star is a minimizer for f for our optimization problem. So what do we do?
We start out by expanding the qxk term and try to see to compare with general xk with the minimizer x star and see what comes up. Let's see.
Okay, so you are saying I'll write f of q xk ck. Okay. P of xk. Yeah. Now.
Uh, Now we try to compare
Just
a
maybe
general
write
xk with a
qxk ck is less than or equal to qx star ck.
Okay. So this is f of x star plus ck p of x star. Right.
And p of x star is 0.
Sorry, p of x star. Are you talking about feasibility?
No, I got it. Just let's.
Okay, so let me just write what do we want to prove. F of x star greater than equal to q x k c k, which is obviously greater than equal to f of x k because penalty is non-negative.
So X star is feasible, so P of X star has to be 0. Am I wrong?
Uh, x star is x star is feasible, correct.
So P of X star is 0, essentially.
P of x star is 0, correct. So do we have this? Do we have the proof?
No, I think we have the upper bound right now.
No. So what he's saying he's saying P of x star is 0. So this implies q of xk ck less than equal to f of x star. But isn't that what we want to prove?
Yes, exactly.
Yeah, we have one. Yeah. One direction is correct, but we have another part also, right?
So this
But that
comes
is
for free.
apparent, right?
This comes
That
for
is
free, right?
apparent.
Oh, okay, that is also okay. Yeah, we have.
Right. So okay. So this is uh, no, let me just write this as okay. So just once again confirming, if you were to write it precisely, like why is x star the optimal solution of the original problem? Is the question clear?
Yeah, I think we have to assume X star is an optimal solution. No other information has anyways given above has been given about X star. What X star is.
Yes. So you have to be very careful. Yes. So what the reason why I'm asking this is because xk could go to some, I don't know what to call x tilde for lack of better notation. Uh, I am just saying right now, x star is basically some solution of my actual problem, which is p. Now when I am solving the qx comma ck and I get my xk, okay, so why should this imply xk goes to x star? Is the concern clear?
Yeah, means actually just the last part. Can you just repeat again? There was a call that was coming. I had to reject that. Just
Okay, so what I'm
few seconds.
yeah, so my what I'm trying to highlight is, see, you got a sequence xk which is obtained by solving this optimization problem. You minimize this q x comma ck,
Yeah,
right? That is
yeah,
some sequence
yeah,
xk. Why should that
yeah.
converge to the x star, which is the feasible and I mean the
Okay.
optimal point of p? Why should that be the case? I mean, if it happens to
Means
be
with
the
the
case, sure, fine. But why should it hold true?
Also, why should it converge in the first place?
Yes, sure. I mean, that's a different thing, correct. But let's just for now, for simplicity, assume that xk converges to, because otherwise there's no point if xk is not
Yeah,
Yeah,
converging.
true.
So let's say
yeah,
xk
yeah.
converges to some x star, some x tilde. Sorry. Why should that x tilde be equal to x star?
Yeah, I think the above theorem should make it make it easy for us to reason about that. Means I was just thinking this the theorem which we just proved the statements.
Hmm. I didn't get you.
No, I am thinking the last four statements which we just proved should help us, I believe, in reasoning about this problem.
No, it's actually much simpler. So let me just write down. So I'm erasing all this. I hope that my concern that I'm sharing is clear.
Yes, it's clear.
Okay, so what we will do is the following. So it's again going to be two lines, and it starts with a very simple observation. So what we are really interested in is f of x k. Let's try to establish the upper bound. So first one is pretty trivial by the non-negativity of the penalty function, which is this p of x k. Okay, this is nothing but your q x k c k. So this part is coming for free. Now again, let's just recall what is xk for q is the minimizer for this q xk ck, right?
Yeah.
So you put so if I put any other point other than xk, what happens?
It is greater.
Okay. Now you can
Yeah.
use the fact that x star is visible. Is the distinction clear? This is very important. We did not say that xk is going to x star.
So X star is some solution of the original problem that we know.
Yeah,
It's
so
not.
we are just mainly distinguishing between for q xk ck, for q x ck the minimizer is xk, right? What we are interested in is x star. So if it's not like we are saying xk is going in limit to x star. Is it fine?
Yes.
No, yeah, yeah,
Hey,
yeah. I
if
got it.
you
Got it.
allow something, I got a good proof with of that earlier theorem in lecture 220. If you allow, I can share. It is from MIT only. That does make sense.
Okay. Yeah. So let me just finish this train of thought and then we can come to it. Exactly. That's fine. Uh, Actually, I was just coming to that. I think I saw an argument which probably makes sense. So let me just quickly go through that, and if it is different, then we can. I'll just hand over the screen sharing to you. Okay. So now that we have characterized what's happening at its as subsequent iterations for Q, P, F. So let's just look at this statement that the professor had made. So in lecture 20. So suppose F uh, f and what are the constraints are taken? H, I think. H are continuous functions, and xk is obtained by solving q x c k. Okay. uh, then any limit point x bar of xk minimizes the original problem p, which is minimize x f of x such that h of x equals to 0. I mean, in general, you can put the inequality constants as well, so it doesn't matter. So xk goes to x bar, and f is continuous. So this implies f of xk is f of x bar. Okay, and right, and what we saw above which is q star, which is nothing but the limit k tends to infinity q x k c k. This is less than equal to f of x star. This is just coming from the where is it? The fourth statement that we have done. So just take a limit here. These are finite values upper bounded, so it will have a limit. I mean, it's monotone. It is bounded above by finite quantity, so the limit exists. So I'm not writing that. I hope that is clear. So therefore, limit k tends to infinity ck pxk is going to be nothing but, I'm just using definition of qx comma ck. So limit qxk ck minus f of xk. I take a limit of this. So what can we say about this? How do we apply the limit here? Just a bunch of continuous functions, right?
Yeah.
So what do I write? I can just take the limit.
Take
I
the
can just sum over the
yeah
limits, right?
yeah
Q star minus f of x bar,
X.
right? F is continuous, q is continuous, and I know the limit of q, q x k c k. Is it fine? Hello.
Yes.
Yeah, it looks okay. Yeah.
Okay, but ck is going to infinity. So what can we say now? This product is happening to be some finite value, and
Yeah, so
then
that it tends to 0, the penalty.
okay. So what is this? P of x bar is 0. What else can we say? F of xk is less than equal to f of x star for all k by definition. That also we saw in the previous lemma. So what can I say here? Here also monotone sequence f of xk's that we saw here, bounded and monotone sequence. F of xk is
Yeah,
strictly is increasing, monotonically increasing, and
yeah,
is
non-decreasing.
so their limit exists. So f of x
Limit
bar
exists.
is less than equal to f of x star. Okay, but x star is the local minimum. So x bar is also an optimal solution.
But how do you ensure that X bar is feasible in the first place?
Feasibility will come from here, right?
Okay. Sorry. Yeah.
So p of x will contain your constraints, right?
Yeah, got it. Yeah, my bad.
So yeah, so you were saying you have some proof. So I mean, I guess this is one way to prove this statement.
Yeah, I had a similar approach, so no difference.
So is this how they handle the limit argument?
Yeah, exactly.
Okay, yeah, I see. I think this is where the argument was inverted, if I understand correctly. I don't know. I mean, maybe they
Mm,
wrote it like this, but somehow it was not clear to me at the time when they wrote it like that. Because unless and until this step is clear, applying this doesn't make sense. I mean, I'm not sure how the conclusion was made in that UCI notes.
No, in the previous node, yeah, as you were pointing out, yeah, it was the limit taking operations are not clear at all.
Right.
In which sequence they were taking the limits. I also had a cursory look at those. Yes. but this yours is a cleaner one.
Okay. So I will get back to the assignment questions. I think that was a long detour. So are there any questions before we move ahead? Okay, I will take that as a no. I will move on to the question number 4. Lagrangian augmented Lagrangian method is primal dual. Okay, not sure why this is being asked, but yeah, it's clearly true, right? I am adjusting for both the primal variable and the Lagrangian multiplexes, right? Okay. Fifth one is saying in which of the following cutting plane method may perform poorly.
Swami, there is a lot of noises coming.
Maybe. Yeah, sorry about that. It's just a fan noise.
Right, so yeah, I'll just quickly write down the options and let me know what do people think about this. Yeah, so any thoughts how to go about this? Hello?
Yeah.
So yeah, I mean, I understand it's just a one-liner, but okay, just
Yeah, we so the cutting plane method, we just go back to the definition. This just tries to approximate some convex region, right?
hmm.
So we try to see what comes close to a convex region. So the third option is disjoint, right?
It's not disjoint. It's just
Means
that it's not a convex region, so it might have
yeah.
difficulties there. Yeah, I mean, there's nothing much to discuss. It's just that the visible region is not really not convex here. Just think of the stuff outside the disk. That's your visible region. So you might find it difficult to find the separating hyperplanes.
So Deep, I just had a quick question about this.
Yeah.
So are these methods equally fast, or some of them, the cutting plane method and the interior point methods, if we compare in terms of computational complexity, the number of steps required? So
Uh,
are they
okay, good
are
question actually. I am not sure to be honest. I've never used these methods myself, so I have no
uh,
clue actually how fast or slow they are.
yeah, means how efficient are they in terms of number of operations? So I was just thinking.
Okay, question for me. So, how efficient are these cutting plane methods? Yeah, I'll get back to you on this. Yeah, thanks for the question.
Yeah, thank you.
Right. Okay. Question is, what is the Jacobian for this? Okay, I guess just fairly straightforward. Yeah, so let's just leave it at that. I think the correct answer is A. It's nothing to do here. Okay, this might be somewhat useful. So I have a multivariate function and a multivalued function. Vector valued multivariate function. Jacobian matrix. So they're asking about the nature of the Jacobian matrix. So there are a few options. Invertible but not necessarily symmetric. Symmetric but not necessarily invertible. Invertible and symmetric, and D is neither invertible nor symmetric. So yeah, so whichever you are saying, if you are saying something is no, then you have to give some counter example.
So I would go with D. Okay.
You'd go with D.
Yeah.
Okay.
No. So D means neither invertible nor symmetric, right?
Yeah.
Yeah. That one. Not necessarily symmetric and not necessarily invertible. I'll go with that.
Why do
So
you? So okay, let's
so
write the Jacobian. So you are saying that. So how will you write the Jacobian? X1.
yeah. So those
Xn.
yeah. Similarly for the other rows.
So you just stack the rows, right? Fn xn, yeah. Yes. So yeah, you were saying.
So if it has to be symmetric, then means the function are totally unrelated to each other. F1 and Fn. So we cannot reason in any particular fashion about.
But can you give an example?
Right? Yeah, example we can cook up something. So
you are right. It's true, and you can just take this example that's given before.
yeah, okay.
So what you can do is you have 1, 2. So you can choose x1 as -1 and x2 as 1. So you have 1 minus 2. One second. Okay, you can take half. X2 as you can take half. So 1 minus 2, and you have 1 minus 2. You got what I'm saying, right? So
yeah, I get it.
Let's take Jacobian 1 2x2, 2x1 minus 2, x1 to be 1,
Yeah. So neither.
x2 to be 1 by 2. This implies j is 1 minus 2, 1 minus 2.
x1 to be -1.
Oh yeah, sorry. x1 to be -1. Yeah, thanks. Okay. Right. Question 8 is saying you have 3 types of optimization problems: least squares, linear program, and quadratic program. So least squares is minimized is ax minus b norm squared. Linear program is minimize x, c transpose x such that g x less than equal to h. And the quadratic program is saying minimize x, minimize this norm, and the constraint is what you would have in a linear program. Okay. So, by the way, just as an aside, since we are on this, so what's the difference between, yeah, what's the difference between solving this, minimize the norm of x squared, so this is 1, and 2 is minimize ax minus b squared. What's the difference between these two types of solving these two types of problems? When would one want to solve one or the other? Any thoughts? So while you think, I'll just write down the options for this question 8. Okay, yeah. So now that I've written the option, I can just come back to this point. Just as an aside, but thought it'd be nice to just recall what under what conditions would we want to formulate one as our optimization problem or two as an optimization problem. Any thoughts? I hope you can hear me.
Yeah, you're audible.
Okay. Are they the same?
For what is the question again? Are these two equivalent?
I mean, okay, that's one question. That's possibly one question, but I am asking in general, when would you want to use problem 1 or problem 2? When would you want to solve for problem 1 or problem 2? Or is it fine? You can solve either of them and it's fine. Like you said, are they the same problems?
I don't think they're the same problem, first of all.
Sorry?
I don't think they're the same problem,
Right.
first of all.
Okay, fine. So in that case, what would be situations where solving one would be preferable as opposed to two and vice versa? Or is there such an advantage offered by one of these in any situations?
No, one will be preferable if when means when Ax is equal to B is probably an underdetermined system.
Okay.
So maybe we want a least norm solution in that case.
Okay.
And probably when Ax minus B doesn't afford a solution, as in least squares approach,
Right.
so then probably 2 has a better advantage. I'm just thinking out loud here.
Yeah, that's pretty much it. So for one, what all that you're saying is you have solutions, but it's a fat matrix. So
Yes, yes,
you have null space that is non-trivial, which means that
yes,
you have a
yes,
solution, but you want to pick one. So this is one way
yes,
to pick it. You could
yeah,
pick a norm of your choice, and depending
yes,
on the
yes,
physics of
yes,
the problem, you could end up solving this.
yes,
What two is saying is that I unfortunately B I have a B which does not lie in the column space of A.
yes,
Okay,
yes,
so all that I
yes,
want is a in the least square sense.
yeah,
I want an orthogonal error. I want a
yeah,
projection uh, of B onto the column space of A such that the
column
error
space
is
of it.
orthogonal to this column space.
Yeah,
Okay, that's all.
yeah,
So
yeah,
this is just saying that I unfortunately have a tall matrix, which is a full rank. Typically, that's what
hmm,
we assume for solving this. Okay, so you have more equations than the number of variables. Uh, yeah, and you want to find an x such that you get at least the closest such b hat.
yeah, precisely.
Okay, the orthogonal projection of b on the column space of a. Okay, so that, I mean, there's a difference. It's not like we just formulate it for no particular reason. So depending on what kind of matrix you are given with, you would want to prefer solving one or the other.
Yeah, yeah,
Okay, so coming back to the question, uh, which is we are given three types of optimization problem. One is the least squares, there's a linear program, and then there's a quadratic program. LS, LP, and QP in short. And the question is simply asking what type of algorithm you would prefer to solve each of these problems. So how would you go about this? So see, is this an unconstrained or a constrained problem?
yeah. Unconstrained.
Right. So there, what can we do?
We can use plain vanilla gradient descent.
Yeah, there are no constraints, so I am just going to use. So there's no need for me to really stick to penalty or anything else.
Yes,
So
yes.
let's come back to LS at some other point, at a later point. Let's focus on the linear program. So linear program is a convex problem. This is a polyhedron. It's a
Yeah.
linear function. So what kind of method would we prefer?
So either interior point or cutting plane. So here interior point is given.
Here, interior point is. Okay, so for now it's a tussle between interior and cutting plane, right? Which is all the options actually. It doesn't really help remove anything. So okay.
Yeah, the
Well,
quadratic program.
except
Yeah, the
for this,
quadratic program.
this one is gone because I don't need to use penalty for least squares. So I am left with B, C, and D. So let me just mark this. So yeah, we are left with three options. Yeah, you were saying something about quadratic program.
Yeah, that may help break the tie. That's what I was telling.
Um, yeah. So how do we go about that? So how will it break? So for example, this quadratic program, what would be suitable?
Quadratic program, we go for the penalty, right?
Uh, why is that?
Yeah, because we have a constraint, right? We have a constraint. So uh, we,
Constraint is there in LP also, right? Okay, but anyway, so you are saying that LP anyway don't have that option of, at least in this case, of using penalty. So you
yes,
are saying penalty. Okay, so
yeah,
the gradient descent would not be preferable, surely, because so that means this is gone. So I can't use D. Okay, because I have a constraint. I could do much better by solving by solving the problem using penalty methods. Okay, what else can I remove? This is also wrong, right? Newton's method. I have constraints here.
Yeah, so we cannot use Newton's method. Yeah.
Okay, so let's just do a sanity check. Gradient descent for an unconstrained problem, sure, no issues. Interior point method for a convex problem, yeah, no problem. Uh, Penalty method for a problem with constraints, yeah, no issues. So seems good to go. Okay. Right. Linear program is given to us. So interior point method for solving an LP, and okay. So if you recall, we had an LP which was saying, I mean the primal dual. I'm just writing the primal dual to set up the notation. So S are my slack variables. So we saw, right, in earlier lectures, some maybe after lecture 12 or something, I don't remember the exact number, but we saw optimality conditions for linear program. What were they? A transpose lambda plus S equals to C, X equals to B, X, S greater than 0, greater than equal 0 obviously, but then there was complementary slackness as well. Okay. So
Yeah.
how did we formulate the problem for interior point methods? I have to solve for the roots of this. And obviously,
Deep,
yeah.
I have a small question clarification.
Hmm.
So in some of the lectures I saw, means one lecture, that the one transpose which is given at the beginning of the last row, they omit that and write essentially as a vector, the x, s, and I. They just constitute as a vector of zeros.
I did not get you.
No, no. So in the last, the last row is formulated as a scalar, right? One transpose x, s, and I, right?
Yeah, so X is basically X1,
Yeah,
Xn,
yeah. Whatever
zeros.
is diagonal. Yeah, yeah.
S is S1, Sn.
Yeah.
Yeah.
They just use the three terms x, s, and then I as
It's not
identity
I
marker.
mean, it's 1. It's
It's a one. Sorry. It's a row of ones.
yeah.
So they just use three components: x, s, and a
No,
row of ones.
XS1 has to be a matrix, right? X1, S1, X2, S2.
No, that is a vector, right? X, s, and one.
X, S, and 1. You mean the product of these three, right?
Yeah, product of these two. This is a vector.
Yeah, so let's just write it. So X, what is XS? That is just X1, S1,
Product of yeah,
Xn, Sn, 0, 0, done, right?
yeah,
Times
and
1,
the row of
1.
ones. Yeah,
So what will this be?
it's just x1, s1. Yeah,
Correct? It's a vector?
yeah, yeah. It's a vector.
Right.
So they write this thing as one of the components of this matrix. Uh, okay. Yeah. Okay. This is not possible. Yeah, but somewhere I saw like this written. That's why.
No, I don't think I got you.
No, I am telling the leading one. They omit the one transpose right at the beginning of the third row.
Yeah, but the way he has formulated, he needs it to be a
Yeah,
scalar.
means yeah. He formulated it as a scalar. So yeah, that's why it's
Yeah,
needed.
so I mean, that actually leads to the question. So the point is, So the claim is 1 transpose xs1 equals to 0. It implies xi to be 0 for all I. Is this true or false?
No, this is clearly false. You can give a simple counterexample.
Okay. So I mean, in summary, the point is, it's not just this 1 transpose xs1 equals 0, but x and s greater than equal 0, which imply
Yeah. Combined with that too, it will imply that too.
okay. So I mean, there's nothing much to do here. Okay. 10th is saying, for which of the following do we need to solve optimization problem explicitly at each step of algorithm? Penalty methods, augmented Lagrangian methods, cutting plane methods, and interior points for LP. Yeah, which one is it?
So I believe that it's the interior point method, right? Because we just go for a Newton's step.
Yeah, I mean, you need to solve the system of equation, right? F of x lambda is
Yeah,
equal
it's
0,
just
and of course you ensure x comma x greater than equal 0. So it's just by definition. Okay. Last two questions. So in the interior point method, algorithm searches for solutions by checking each extreme point of feasible region. So is this true or? Is it true?
so this is false, right?
Yeah, it is actually false, because that's the point. We are avoiding
Yeah, you're avoiding
simplex.
this thing, the extremities, right?
Yeah, we are trying to avoid simplex because it'll just get stuck in these extreme points.
Yeah.
I mean, looking
So
for all the
so
extreme points.
so that's the reason why it tries to adopt a central path, right?
Okay. Any optimization problem can be transformed into ALLP. So how to can we do this?
I am not sure regarding this. Let's see if we could.
Okay.
So Professor Kulkarni was discussing that we could turn a problem into a linear problem by absorbing the those things into the constraints. But I'm not sure about this, how to go about.
But if the constraints already have a non-convex
Yeah,
region.
exactly. Yeah. I mean, it's not, so the problem is not about, so if you could write x such that, so this you can just write as minimum t greater than equal to f of x, t x, x belongs to s. But like he said, if x belongs to x, this itself happens to have non-convex constant, then what can you
Yeah, true.
do? Okay, fine. So yeah, clearly is false. Yeah, so we have a few minutes left. If you people have any questions or if you want to solve some other things, and you can try out a few more things. Just try verifying this if and why this is true. Let me go back to it. This point. Why should this be true? So
Because the limit is finite. So isn't it obvious?
yeah, but how will you prove it? Just the proving exercise for limits. So I have limit pk qk equals to some, I don't know, d, and pk goes to infinity. So maybe I should not use pk here. Use ak pk, ak goes to infinity, and obviously d is less than infinity. We need to show this. Just try this out.
So probably a proof of contradiction may be easy. I mean, I'm not.
Okay, so you are saying you want to go in that direction.
Yeah,
So
I
you are
mean,
saying P
suppose.
implies Q, you want to go by contrapositive. Sorry.
Yeah, I mean, I suppose that
Not
pk
Q
is not.
implies not P.
Yeah, not p. Yeah,
So okay, you are saying limit is not 0.
yeah, and try to see what happens after that.
Okay. Just try it out.
Yeah. Fine.
Okay.
Just a simple question for the convergence theorem for the L1 penalty.
Convergence theorem for L1. Oh yeah, okay, yeah. Yes.
This again might look like a simple question, but they just came up. How do you find C star if you don't know X star in the first place? So
Uh, okay, so okay, your question is how do I in practice find C star, right?
yeah, how do you go about this
Okay,
algorithm?
right. So I don't think the point for this is to uh, say that I know how to find C star. I think it's just trying to say that you can for a finite value actually do it. That's all. Finite value of C, and as long as it's more than C star. So the theorem is not
But
trying to tell you that this is how you can find the value of C star.
so any algorithm exists that does that? Are you aware of?
I am not sure what heuristics they have for picking C star. Let me think. Choosing C star. I don't know about that. I think.
And let's say we know some heuristics to start with for C star,
Okay.
but then
Yeah, you were
reverse
saying.
implication. We again do not have the reverse implication that X star being the local minimizer of the penalized objective. will also be a local minima of the constraint problem.
Yeah, so you are asking for necessary and sufficient conditions. You want to completely characterize what it means to say I am at an optimal point, right? Yeah, so
Yeah,
that's generally very, very hard because you can't, unless until you assume something very specific about the functions.
yeah, but in the lecture, sir did assume, I guess, that if I'm finding the minima for the penalized function, that will be the minima for that as well. I mean, extra.
Okay, just a slight point there. So, like we derived earlier in the
Yeah,
discussion, so it
for
doesn't
the
mean that that limiting point has to be feasible. If it's feasible, then great. Actually, it's doing what I expect it to do. It doesn't have to be feasible.
okay.
It can minimize the objective function, sure, but it doesn't have to be a feasible point because xk going to x star y is not required to be in that feasible set S.
Yeah, okay.
But yeah, I mean, regarding what you're saying, unless until I think if you assume function to be strongly convex and all kinds of things, Lipschitzness and whatnot, I don't think you can hope to have a necessary and sufficient condition. So just like in
Oh,
convex, for example, whatever proofs you have seen, the first order conditions are necessary and sufficient, right?
yeah.
So I don't think other than such functions you can even hope to get the implication in the other direction. Already, first of all, it is assuming too much because you are saying that only under the assumption that xi is a strict local minimum, not a regular local minimum. The local minimum
Okay.
has to be strict. So in that region, at least it has to be somewhat convex.
Mm, okay.
Okay, right. Okay, one more question for me is
The
how do we
yeah,
pick?
the
Yeah.
we have something at the beginning also, right? One part was left, so we are not sure about.
Okay, yeah, just a second. I'll come back to it. So one more thing, I need to check how to choose C star for L1 penalty. Right, yeah, I think there was some question that. What was the question? Well, I mean, we kind of discussed this. Yeah, so when we are solving this problem, qx comma ck, so that point, does it have to be a feasible point for the minimization problem? We already somewhat talked about this, right, when we were proving these statements.
Yeah, we discussed somewhat. Yeah,
So especially in the proof of 4, where I was asking what assumptions are we making about x star and what is the limit point of xk.
yeah. Means yeah, it's not necessarily true. Yeah, I get that. Yeah, there were certain assumptions. Yeah.
All right. Uh, so yeah, we can stop here unless you people have any questions. Hello.
Yeah, I don't have any questions from my end.
Okay. Uh, Tanmay, do you have any questions?
No. That.
Tanmay, sorry.
Yeah, yeah.
Okay, so we can stop here if there are no questions. I'll stop the recording.